Welcome to this lecture series in real analysis. In this lecture, we'll introduce the notion of one-sided limits and see an example, or rather a class of examples where they exist. So we need to know what is meant by the limit of a function in order to be able to digest the definitions very well. And this is the definition for, there are some 4 kinds of limits that we talked about in the previous lecture, or on the lectures on limits, and this is one of them. There were other variants, and I do not want to get into the details or explain this here in the recall. You can go back to the lecture if it is confusing. It is important to be comfortable with the notion of limits and understand it properly before one proceeds too further ahead in this lecture series. Okay, so with that, let me continue. Here are some problems for practice. And now let us get started. So we will define one-sided neighborhoods and one-sided accumulation points. And then we will define what is meant by one-sided limit. And then see examples, or at least a class of examples. So fix a point x in R. Then a right neighborhood of x is, you can guess, but let me first explain via picture. So a right neighborhood of x is any set of this form. It contains x, it doesn't contain anything towards the left, and it is, apart from this discrepancy that it doesn't have anything on the left, it is like an open set. So it contains x and then you have a neighborhood, the other point. So I will define precisely. And here this picture kind of suggests that this thing is one contiguous thing, but that need not be. By this definition, you can include things which are further ahead and disconnected with this part. Anyway, so let me define. So a right neighborhood of x is any set of the form of this form where U is a neighborhood of x. So what is a right neighborhood? Just take any neighborhood of x and truncate it. Throw away the things which are on the left side of x, left side of x, and that's it. That's a right neighborhood. Very simple definition. And now, naturally, we will define the delta right neighborhood. Fix a positive delta. The delta right neighborhood of x is, in pictures, it is going to be this interval. And if you write it formally, it's not much different. Is the set, that one. So that's the delta right neighborhood. And now we can talk about right deleted neighborhood of x. Pictorially, it is, since it is a deleted neighborhood, it will not contain x. But apart from that, it is a right neighborhood. So the formal definition would be a right deleted neighborhood of x is any set of the form U intersection x comma infinity, where U is any neighborhood of x. Okay, very simple definitions. Lastly, the delta right deleted neighborhood of x. The fix a positive delta. The delta right deleted neighborhood of x is the following interval. That's it. And you can draw your own picture for it. Alright, so pretty simple definitions. And now with those definitions, we will define what is meant by a right accumulation point. And then you can similarly define for yourself what is meant by a left accumulation point. So fix a subset of reals, non-empty. And fix any real number, doesn't have to be in the set S. We say this guy is a right accumulation point of S if heuristically or intuitively what we are trying to capture is you can reach x naught with the points in S which are simultaneously on the right side of x naught. So using the points of S you can reach x naught, but only those points which are on the right side of x naught. I mean, the points in S that you will be using to reach x naught are the points which are on the right side of x naught. That's heuristically the thing that we are trying to capture. And the definition is very simple. So we say x0 is the right accumulation point of S if every right deleted neighborhood of x0 has a point in S. Right? So if you understood the definition of an accumulation point discussed when we were, or maybe it was 2 lectures ago, so if you understood that definition, this shouldn't cause any problem. And now note that every accumulation point is obviously a right accumulation point, a trivial remark. Every accumulation point of a set S is also a right and a left accumulation point. What am I saying? Every right accumulation point is an accumulation point. This is completely wrong. So what I meant to say was that every right accumulation point is also an accumulation point. And similarly, every left accumulation point is also an accumulation point. You should come up with examples where an accumulation point is not a right accumulation point. Very easy to come up with such an example. Okay, and there is another thing I want to say, just a small example, that B, so I think I'm going to give that example that I wanted you to give. So B is an accumulation point of the interval a comma b, but not a right accumulation point. Okay. So with this, we can define what is meant by one-sided limits. So again, fix a function from a set S of reals to reals, and fix a point in the reals, which is the right accumulation point of S. Okay. Then we write this expression. There is a little plus here to denote that we are defining the right limit. We write this expression to mean, where L is a real number, we write this expression to mean that for all epsilon greater than 0, there exists delta greater than 0 such that if x is on the right side of x0 and x is in the domain of the function and it is also in the delta neighborhood. So all this much says is that x is in the right delta deleted neighborhood of x0, and this just says that x is in the domain of the function. So with these constraints on x, we must have that fx doesn't betray epsilon too much. Doesn't betray L too much, which respects L with a tolerance of epsilon. And I would like to explain this via picture and all that, but if you follow the definition for the standard limit, the usual notion of limit, not the one-sided one, but the traditional limit or the vanilla limit, then you can easily draw a picture for yourself. So I don't want to spend time on it. Okay, and here is another exercise for you that define this expression, plus infinity or minus infinity. So this is an exercise. Okay. And here is an example where we can see a one-sided limit in action. So we know that, for instance, let's say we consider this point. Let's say that is, this is the graph of the greatest integer function. So this is 1, this is 2, 3, and the values are also, so this is 0, this is 1, this is 2, and so on. So we know that the function does not have a limit at this point. This limit does not exist. But we want to see that the right limit exists and the left limit also exists, but let me just argue that the right limit exists. And we claim that the right limit is actually equal to 1. So why is that? Well, fix an epsilon. So let's say we have fixed an epsilon and I have drawn an epsilon band around this point 1. Can we find a delta can we find a positive delta such that whenever we choose x with this constraint is automatically satisfied because S is the entire set of real numbers. So let's just focus on this part. Can we find a delta such that whenever x is in the right delta deleted neighborhood of 1, this happens? Of course we can, because you can just take delta to be half. If you take this delta deleted neighborhood, all the points of this neighborhood map to 1. They are actually, the function value is equal to 1. There is no need of any tolerance or anything. The function is on the nose equal to 1. So this criterion clearly holds, and the right limit at the point 1 is 1. What about the left limit? The left limit is 0. The right limit and the left limit, they disagree, but they both exist. Okay, ponder upon it if this is not clear. Alright, and now let us recall a little bit about monotonic functions. So this we discussed when we were discussing monotonic functions. We have a function, we say that it is increasing if y is bigger than x, implies that the function values are also in the same order, and strictly increasing if the inequality is strict. Similarly, you can define decreasing and strictly decreasing functions. Here are examples of increasing and strictly increasing functions, suggestive examples. And lastly, we say f is a monotone function if it is either increasing or decreasing, and strictly monotone if it is strictly increasing or strictly decreasing. Okay, so with this recollection, let us move to the main point of this lecture. Or yeah, before we go there, let me just mention these two examples. So these are examples of increasing functions. This looks like a strictly increasing function, while this is just an increasing function. Okay. So here is our main lemma that we want to show. So we have a function from reals to reals, and assume it is a monotone function. Then we want to show, let me change the color. Then the left and the right limits of f exist at each point of the domain, or at each real number. What does that mean? What this means is, just to kind of reiterate, it just means that for all real numbers for all real numbers, there is some other real number such that this equation holds. And similarly for the left limit. So I should have, the choice of the symbol L is a bit fishy, because this may suggest that we are talking about the left limit or anything. No, it's just, don't get confused. There's a plus here which is denoting the right limit. So, and similarly for the left limit. So, ... Okay, so for monotone functions, right and left limits always exist. That is the point. And the proof is not hard or anything. Take this as an exercise before we discuss the proof in detail. And we will understand the proof by means of these two examples. Okay, so first, without loss of generality, assume f is an increasing function, because the ditto same proof can be written for decreasing functions. And we will only show the existence of right limit. Everything else is an exercise. So we will show that this thing exists. So I should have, before writing that statement, I should have said fix some real number x naught. Okay. So now assume on the contrary. Yeah, so not assume on the contrary, before that. In fact, what we will show is that we can nail down this limit. So we claim something stronger. define some quantity which let us motivate that using the graph. So consider this increasing function, and let's say this is my point x0. What should be the right limit? So what you do is you look at the function on the right side of the point x0, and what you will see is that it is decreasing and becoming to some sort of wants to become some value. So naturally we should like to say that the right limit at the point x0, if it is anything, it has to be the infimum of all the values that the function takes on the right side of x0. That's intuitively suggested by this diagram, and that is what we will end up showing. So define this quantity L as the infimum of all the values that the function takes on the right side of x0. Right? So let me put a star here. This is the definition of L, and we claim that this expression is equal to L. So once we prove this, of course, this is proven. This is proven. Okay, so now assume on the contrary. Assume on the contrary that this limit is not equal to L. Whatever it might be, even if it doesn't exist, that's fine. All we are saying is that assume this is false. Then, by definition of the right limit, there must be some epsilon. There exists an epsilon for which no delta works. No delta witnesses the faithfulness of the function f to the number L. More precisely, that is, for all natural numbers, there is some point in the corresponding right deleted neighborhood. So here there is an n, but here there is 1 by n. So we are kind of shrinking the neighborhood. So for each n, you can find xn, which is an offender, with the property that f of xn minus L in the absolute value is greater than epsilon, or greater than equal to epsilon. That's also fine. Okay, so now since f is increasing, we deduce or we infer that. So how do we deduce this? Well, what is the definition of L? L is the infimum of all the values of f on the right side of x0. Now xn is on the right side of x0. So whatever is the value of f on this point, that cannot be smaller than L. Or so this is definitely a positive number, and therefore we can drop the absolute value sign and write this. So we have that because of the increasingness of f. So therefore, just rewriting it. Okay. But now note that xn converges to x0, and therefore, since f is increasing, we see that fx is at least L plus epsilon for each x greater than x0. So why is this? Let's try to understand that in the context of this picture. Suppose x0 is this point. It could have been any other point, but I'm deliberately taking it specifically this one. So why do we have that this is the case for each x greater than x0? Fix some x which is greater than x0. Now since xn converges to x0, there is some xn sandwiched between x0 and x, And the value there is at least, the value there is at least L plus epsilon that we deduced. So the value there is at least L plus epsilon, and since now f is an increasing function, the value at x will also be at least L plus epsilon. So this is justified. Okay? But then this implies that the infimum of fx as x is greater than x naught is also at least L plus epsilon, but this infimum is by definition equal to L. So we get L is at least L plus epsilon, which is a contradiction. Alright. So we see that monotone functions have this nice property that left and right limits always exist. They may not be equal, like in fact in both these examples the left and right limit differ, but they exist. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.